This is the first video for week number 11. So in this video, we look at continuous functions on intervals. Let's begin by looking at this example. Let A be a subset of R and consider a function f from A to R. We say that the function f is bounded on A if there exists some constant m bigger than 0 such that the magnitude of f of x is less or equal to m for all x in A. That's what we call a bounded function on a subset A of R. As a first example, let's take A to be the closed interval from 0 to 2, and let f from A to R be defined by setting f of x is equal to x squared. Then we see that if x belongs to the interval 0 to 2, then x squared lies between 0 and 4, and therefore f of x lies between 0 and 4 for all x in A, and so that tells you that the magnitude of f of x, okay, is less or equal to 4 for all x in A, so that f of x is bounded by 4. In this case, 4 is our m. Okay, so our constant m is 4 in this case. The second example, we have A as the open interval from 0 to infinity, and then our function f from A to R is defined by setting f of x to be 1 over x, okay? Then we claim that this function f is not bounded on A. And the reason is that if we pick any constant m bigger than 0, and we set xm to be 1 over m plus 1, then clearly xm belongs to A, okay? Xm belongs to A since xm will be a constant bigger than 0. Now, if you apply f to xm, okay, you get that f of xm is equal to m plus 1, and this for sure is bigger than m, okay? And therefore, given any constant m bigger than 0, right, you will always get an element xm, okay, in A, such that f of xm is bigger than m, right? And so if you take the magnitude here, since both m plus 1 and m are positive, if you take the magnitude here, you end up with the fact that the magnitude of f of xm, you end up with the fact that the magnitude of f of xm is bigger than m, so that f is not bounded on A. Why? Because for every constant m bigger than 0 that you pick, okay, you will find an element xm, right? You will find an element xm in A such that the magnitude of f of xm is bigger than m. Next, we look at what we call the boundedness theorem. So let I be the closed bounded interval AB, and let f, okay, be a continuous function on I. Let f be a continuous function on I, then f is bounded on I. Then f is bounded on I. What this theorem is telling you is the following. If f is a continuous function on a closed bounded interval I, then f is bounded on I. that every continuous function on a closed bounded interval I is bounded on I. That is, in short, that's what the theorem is telling you. So let's look at the proof. And we are going to do this by contradiction. So let's assume that f is a continuous function on a closed bounded interval I, and that f is not bounded on I. Then, if f is not bounded on I, then for every natural number n that I pick, right, there will be an element xn in I. Please note that this is I, not n. Replace this by I, okay? So if what I was saying is that if f is not bounded on I, then for every natural number n that I'll pick, there will be an element xn in I corresponding to this natural number that I've picked, right? Such that the magnitude of fxn is bigger than n. And this will be true for every natural number n that you pick. For every natural number n that you pick, you'll get a corresponding element xn in I, such that the magnitude of f of xn is bigger than n. Now, since each xn is in I, okay, since each xn is in I, that means since each xn is in I, that means a is less or equal to xn, and xn is less or equal to b for all n. So in that way, we are generating a sequence xn, okay, which is bounded because each xn is in I, and therefore you have that a is less or equal to xn, and this is less or equal to b for each n. Okay, since I is the interval from a to b. So that means the sequence xn is bounded. Now, since the sequence xn is bounded, right, the Bolzano-Weierstrass Theorem tells me that this sequence xn, right, has a convergent subsequence, which I'll call xnk. Okay? Now, since xnk is a subsequence of xn and xn is bounded, then xnk is also bounded. In particular, since each xn lies between a and b, then each xnk will also lie between a and b. Each xnk will also lie between a and b. Now, since xnk is a convergent sequence, let's assume, since xnk is a convergent subsequence, let's assume it converges to x. Okay, so let's assume xnk converges to x. Since each xnk lies between a and b, then the limit of the sequence xnk also lies between a and b. In other words, what we are saying is that a lies between a and b. How do you see this? Since each xnk satisfies this inequality, right? You just look at this as a constant sequence, an. Look at this as a constant sequence, bn, where each bn is equal to b, and here where each an is equal to a. Then the limit of the sequence an is equal to a. The limit of the sequence bn is equal to b, right? X and k lies between an, right, and bn, right? So that the limit of x and k lies between the limit of an and the limit of bn, right? The limit of an is a, and the limit of bn is b. So that simply tells you that the limit of x and k lies between a and b. The limit of x and k is x, so x lies between a and b, and that is what we have here. Since x lies between a and b, that means x belongs to I, because I is simply the interval ab. And since x belongs to I, and f is continuous on I, then f is continuous at x. Also, since xn converges to x, okay, and f is a continuous function, then I'll say that again, since xnk converges to x, okay, and f is a continuous function, then f of x and k converges to f of x. F of x and k, this is k, so this will be f of x and k, right? So since x and k converges to x and f is a continuous function, then f of x and k converges to f of x. F of x and k converges to f of x. Okay, now since f of x and k converges, right, then it must be bounded since every convergent sequence is bounded. So we conclude that f of x and k is a bounded sequence, right? But then this contradicts the fact that the magnitude of f, x, and k, right, is bigger or equal to nk for all nk. Where does this come from, right? It comes from this one here. The sequence xn, right, satisfies this condition. The condition is that the magnitude of fxn is bigger than n. The magnitude of fxn is bigger than n for all n. All right? Since xnk is a subsequence of xn and xn satisfies this condition, then x and k must also satisfy that condition. That is, the magnitude of x, the magnitude of fx and k must be bigger than nk. That's what we have here. The magnitude of fx and k must be bigger than nk, right? This one here. But then we know that nk, okay, is bigger than k, right? So the conclusion from this is that for every natural number k that you pick, right, there will be an element, okay, x and k of I, such that the magnitude of fx and k is bigger than k, okay? And this tells you that the sequence fx and k is not bounded, which contradicts the fact that the sequence fx and k is bounded, which comes from the fact that fx and k converges. So this contradiction means that our assumption was not correct. And what was our assumption? Our assumption was that f is not bounded on I. So then we conclude that f must be bounded on I.